So remember what we discussed in our previous video. I did tell you that if you want to calculate the enthalpy change, that is the energy that is absorbed or released in breaking or forming one more of a covalent bond, then if you want to calculate what we called as being the enthalpy change, which we represent by delta H, we did say that the enthalpy change will be equal to, it is simply the summation of the energy of the reactants minus the summation of the energy of the products. That's what you need to remember. So that's the energy of the reactants in this case. So you're dealing with the reactants, and there you're dealing with the total energy of what we have in the products. That's what we talked about the last time. Now I did tell you, by calculating the enthalpy change using bond energies in a reaction, you can tell whether a reaction is actually endothermic or exothermic. And according to what I said in my previous video, I did say that if the energy, let me call that one as 1, if the energy of the reactants is greater than the energy of the products, then what will be your conclusion that you're going to have? Well, such a reaction is actually an endothermic, that is an endothermic reaction. The second one that I talked about is that when the energy of the reactant is less than the energy of the product, then your conclusion that you're going to have is that such a reaction is simply an exothermic reaction. So remember, endo simply means inside, meaning a reaction that absorbs heat from the surrounding. In other words, you take in the heat from the surrounding. The word exo there simply means outside. Outside. So you are simply releasing heat energy to the outside. So basically, this is what you need to remember when it comes to what we are calling as being bond energies. In summary, I did say that if you want, you can simply say that the enthalpy change is simply the summation of the energy of the bonds that are actually broken minus the summation of all the bonds that are actually being formed. So that is what we talked about. So bonds broken is in the reactants, then the bonds that are formed are actually in the product. So you are going to have such an analysis. Well, let's look at some few examples with that in mind. The first question there that I have says calculate the heat of reaction, or the enthalpy change for the decomposition of ammonia. So they were talking about the decomposition of ammonia. So when ammonia decomposes, it produces, in this case, and nitrogen and also hydrogen. So they have given you the bond energies that are there. Now, given the bond energies, what you need to do when it comes to this one, you need to write what we call bond line formula. So how are the atoms bonded in ammonia? How are they bonded? So if I look at that, in ammonia you have got the central carbon atom, which is nitrogen, and we know, of course, that there are single bonds of hydrogen that have actually been attached to it. But remember, how many molecules of ammonia are there? They are telling us there are 2. So it's like whatever I have here multiplied by what? By 2. That's what you should be consider. That is what you should be considering there. Of course, what is being formed, there's a nitrogen, but of course, remember I told you that this equation should be balanced, so we should be able to have a 3 right there because it was not balanced. So nitrogen is there, and of course you know that nitrogen is actually forms a triple bond between 2 nitrogen atoms. So that's the bonding that we find in nitrogen, and there's only 1 molecule of nitrogen. Plus, when it comes to hydrogen, what's the bond? Of course, we know that hydrogen and hydrogen, there's only a single bond. But how many hydrogen molecules are there Well, according to what we can see from the balanced chemical equation, there's actually 3. Let me use a different marker there. So when you write like this, it is actually going to help you now, to calculate, the heat of reaction. Remember that heat of reaction is simply the enthalpy change. That's what they're telling you, the heat of the reaction that you're having. So now when you look at this one, I'll come to this guy we are calling ammonia. How many bonds in this case? Remember, we have hydrogen, hydrogen, hydrogen to nitrogen, nitrogen to nitrogen. So here I need to look at how many nitrogen to hydrogen bonds are there. So I've got 1, 2, 3. So in this case, if you want, we can simplify hydrogen to nitrogen bonds that I have in this molecule. They are actually 3. You can see that they are actually 3. So it's like there are 3, but that 3 multiplied by the 2 that is outside. So it simply means that altogether you are going to find that there are 6. So you have 1, 2, 3, but because there are 2 of these molecules, so that 3 multiplied by 2. So meaning it gives you that there are 6 nitrogen to hydrogen bonds. That is what we know there. Of course, that is direct. We only have 1. There again, when I look at that, we only have 3. That is actually a direct one that we do have. So now what we are going to do is that we can now use the bond energies. What is the bond energy of nitrogen to hydrogen? It is 338. But these bonds nitrogen to hydrogen, they are 6. So it is going to be 6 multiplied by 388. All right. What about for nitrogen triple bond? It is 945. And when I look at hydrogen, it is 436. But how many hydrogen to hydrogen bonds are there? There are 3. Therefore, it will be 3 multiplied by 436. So we just need to multiply that and try to work out. So it is going to be, in this case, 6 multiplied by 388. So that is going to give me a 2,328 kilojoules. All right. If you look at this one, it will be 945 plus, if you multiply 3 multiplied by 436, it is going to give us a 1,308. So we can add the energy on the product side. So this plus 945, it will give me a 2,253 kilojoules. Remember, this is the energy of the products, and this is representing the energy of the reactants. So how do you get, in this case, the enthalpy change? Remember what we said, for you to get the enthalpy change delta 8, it is simply the summation of the energy of the reactant minus the summation of the energy of the product. So what is the energy of the reactant? 2,328, that is kilojoules, minus 2,253 kilojoules. What is that going to give us? Of course, if we try to say 2,328 minus 2,253, you can see what it is giving you. It is actually giving you a positive 75, and that is kilojoules. Of course, this is per mole, so this is the amount of energy, that amount of heat of reaction or heat energy during the decomposition of what we are calling ammonia. Now, if you notice, our answer here is actually positive. So is this an endothermic or exothermic reaction? Of course, because it is positive, you may simply conclude that that is simply an endothermic reaction. So this is an endothermic reaction. Thank you so much for watching. Watch out for some more videos where I show you some more of these examples.